Welcome to the UGC e-Pathshala lecture series in computer science. This is the subject of cloud computing and we are discussing election algorithms. So, today we will discuss the ring based algorithm and we will see how the ring algorithm works in the process of election. We will see how to decide whether the algorithm is correct or not, and we will see the summary. So, in the last class we saw what is an election. Basically, election is nothing but the selection or choosing one among the peer nodes or servers that will have a special kind of functionalities. Now, the next question that we answered is it necessary to have election in cloud? And the answer to that is that it is required to have election in cloud, because cloud consists of many similar nodes, and these nodes need to organize themselves and work for something specific, and for that we need to have election. We also looked at specific election algorithm which is called the Bully algorithm. In this class, we will look at a second election algorithm that is very popularly used, which is called the ring algorithm. So, typically any distributed environment consists of many nodes, and again typically these nodes are able to communicate with each other freely. But when we have a ring structure in place, then these nodes are not able to communicate with each other. Why we want to put this restriction of ring in a freely communicatable nodes is because it is easier to make communication. One node is responsible for communicating with the other node, and thereby it's possible faster to detect failures. In such a ring, we put the restriction that a node can communicate with only one specific node and can receive from one specific node. The problem of putting such ring is that there will be an additional latency in case any specific node wants to communicate with another node which is far off in the ring. So, for the ring election algorithm, this is our system model. We have n processes, and these processes, each of them has a unique ID. We organize these processes in the form of a logical ring. The ring is logical because the nodes may be physically present in different places, and that does not stop us from executing our logical node. The communication alone will be done based on our ring structure. So, let us look at the beauty of having a logical ring. We have in this system 6 nodes having different node IDs, and these node IDs are unique IDs, as we have already said. Now, normally these nodes are capable of communicating with each other freely, but we put the rule that specific node can communicate only to a specific node and can receive from a specific node. For example, in this example, if we say P1 is able to communicate only with P50, P50 will be communicating only to P100, P100 to P30, and so on. Then this forms a ring kind of mechanism which we can look at, that these are our logical ring, and we have the communication channel between them, P1 to P50, 50 to 100, 100 to 30, and so on. So, in this ring, if P30 wants to communicate something to P1, then P30 will have to communicate to P95, 95 to 20, and 20 to P1. So, this is the problem of ring, but having a ring helps in many places, including having an easy election algorithm that we are going to see today. So, for our ring election algorithm, what is our system model? our system model is that there will be n processes, each process having a unique identity using which we can process ID, using which we can see the ring, and the processes are organized in a ring structure, and any ith process is has a communication channel to the next process, which is p I plus 1 mod n. Now, we are looking at the algorithm. The first step says that any process pi will initiate an election. How will it initiate an election and why it will initiate an election? These are the two questions that we have to answer at this point in time. It will initiate an election either because the system requires a leader and a leader was not elected before. The other reason why a node will initiate an election is because it detects that there was already an elected leader, but this particular node detects that the leader has failed and is not communicating with others. So, either of the reasons will make one of the nodes to start an election. We call this node the initiator node for election algorithm. Now, this process, let us assume pi initiates this election by sending election comma pi. So, I am starting an election and my ID is pi message to the next node. Now, any process which receives this particular message election comma pi, if this receiving process is say pj, then pj will compare its own priority with the priority of pi. Now, priority can be set to be anything. In this case, we have taken the node ID to be the priority, which means that if a process has a node ID, if the receiving process pj has node ID smaller than the process from which it has received the election message, then it will forward the message directly to the next node. If pj has a higher node ID, then it will change the election algorithm. It will put election comma pj and will send the message to the next node. Third step of the algorithm says that when a process pk receives back its own message, which means that I am a process, I received an election comma x message from my earlier node, and I, having my ID greater, I changed it to election comma my own ID, and I communicated it to the next to my out channel, and this out channel and all the rest of nodes through which this message will pass, if all of them have ID smaller than my ID, then what will happen? I will receive back the message saying election comma my own ID. So, that is the third step of the algorithm, which says when a process pk receives back its own message, that means election comma my own ID pk it receives back, then pk understands what? That it is the highest process. Why do we say that pk is the highest process? Because if pk is not the highest process, then other processes would have changed the ID. Since pk has received back the election comma pk, it means that nobody after pk has changed the ID, and therefore pk understands that I am the highest node in the system, and therefore I am the coordinator. Now, it will send the coordinator message to the next node, and any process receiving a coordinator message has the job of only sending the coordinator message to the next node, and so on. So, if we look at this algorithm is divided into two phases. In the first phase, we see that among so many nodes, one node is identified to be the coordinator or the leader, and in phase 2 we see that this leader, after understanding that I am the leader, communicates this information to the all the other nodes. So, Our algorithm, the first 3 steps where somebody initiates the election algorithm by sending election comma pi, every pj receiving the election message either forwards the message or changes the value from pi to pj and forwards the message to the next node, and the highest process receives back its own message saying election comma pk. These are the 3 phase 1 steps where we are identifying the specific node which should be the next leader, and the next 2 steps which sends the coordinator message and everybody else forwards the coordinator message till it comes back to the sender is the second phase 2 of the algorithm. Now, we will take an example to understand how the ring algorithm works. For this, we have to decide the legends, and here are the legends. A green colored node is will be considered to be the leader node. If a node has crashed, then we put 2 red lines across and we indicate that to be a crashed node, and this red colored node is an initiator, the election initiator. So, in our example, we can say that P100 is the leader node or the coordinator node. Here in this example, we are seeing P1 and P95 may be crashed nodes. Now, if a node crashes in a ring, then we simply remove the nodes and make the channel from P20 to P50 communicate with it. So, earlier on P20 was communicating with P1. Now that P1 has crashed or is not working properly, P20 is now able to communicate directly to P50. So, anytime a node crashes, be that the current coordinator or be it any other node, we remove that specific node from the ring and let the 2 in between nodes communicate with each other directly. And this is when this example shows that P100 is a leader node and it has failed, and we do the same thing, we remove that specific node from the ring and we continue communicating between P50 and P30. So, with these conventions we are ready to, and of course P20 is the node here which will initiate the election process. So, this color indicates that this is the initiator of the election algorithm. So, with this convention, now let us look at an example of ring algorithm. So, in this example we have P100 which is the current leader, and for some reason if P100 fails, if it crashes, then during this time till nobody has detected the crash of P100, the system goes without having a leader. But since leader is required and nodes will communicate, will at least try to communicate with a leader, one node or other in the environment will decide that the leader has failed. Now, one word of understanding is how can any node other than P50 decide that the leader has failed? It is this way, that maybe P50 is not trying to communicate with the leader, P30 is trying to communicate with the leader. So, P30 would have sent some message through the ring to the leader which is P100, but P100, because P100 has failed, P100 will not respond, and in a distributed system we detect failures by doing a timeout. We already have seen how the timeout works. We set a timeout limit. So, P30 when it wants to communicate with P100, it will send a message, it will time out and it will not receive any reply because P100 has failed, and then it will try this process maybe 5 times and finally it will decide that P100 has failed. So, in our example P30 is the node which decides that P100, that is the current leader, has failed. So, it will do what? According to the step 1 we are supposed to initiate by saying election comma pi. In our example we say election comma p30. So, p30 sends a message election comma p30 to the next node. Step 2 says pj will receive the message, and if pj's id is greater than the sender, then pj will change the id. So, in this case p95's id is bigger. So, the message is changed by p95 saying election comma p95. Now, p20 will receive the message election comma p95, but p20 has less priority or less number. So, it will simply forward the message to the next node. P1 similarly will forward the message to the next node. P50 will also forward the message to P30, and P30 also will forward the message to P95. So, this is the third step of the algorithm, which says that when process Pk receives back its own message. So, in this example P95 received back the message election comma P95, and hence it understands that it is the coordinator. So, P95 now has become the coordinator. Now, after becoming the coordinator, now it has to go to phase 2 and inform all the other nodes that I am the coordinator, because other nodes are not aware of who is the coordinator. So, now step 4 has to be executed, where the new coordinator sends the coordinator message. So, P95 now sends a coordinator message to the next node, and step 5 says that this coordinator message will be forwarded to all the other nodes. So, P20 will forward, P1 will forward, P50 will forward, and P30 will forward till P95 does not receive back the coordinator. Once P95 has received the coordinator, it decides that I am the coordinator. So, this is how the coordinator is detected. Now, let us look at the correctness of this algorithm. As we know that correctness of distributed algorithm, specifically election algorithms, has two parts. One is called the liveness of the algorithm. The liveness of the algorithm says that the election algorithm must elect a coordinator in finite time. Let us define this term finite time a little bit. What do we mean by finite time? If we can calculate the amount of time it is going to take to execute certain thing, then we say that it is being done in finite time. So, a calculable amount, an infinite time on the other hand, will be something that cannot be calculated. So, we have to show that our ring algorithm can select or elect the leader in finite time. That is our first correctness criteria, which is the liveness criteria. And the second correctness criteria says the safety, and in safety we say that exactly one process will be elected as a leader. So, these are the two correctness criteria which we have to verify for our ring algorithm. How can we say that liveness is followed? It is because we are forming the ring. So, we know the distance between two nodes. Let us look at how we know this. We have seen in our communication module that these nodes, typically in cloud, these nodes use the some protocol, either TCP or UDP, and largely we use UDP to communicate. Now, if we are using UDP, then the problem is that we may not be able to determine the amount of time it is going to take, because the packet goes through any channel and there is no predefined path in an UDP protocol in networking. But still, because we know approximately how many hops or what is the distance it is physically going to cover between two nodes, therefore, we can decide that it is a finite time, it will not be an infinite time, and we have our reliable multicast. So, our reliable multicast does what? A reliable multicast will take into account the fact that packets can be lost or network can be separated, and therefore, it will retransmit the same message once more, and it will definitely get a reply if the node is good, if the node is live and there is a communication underlying network is not faulty. So, therefore, for every pair of nodes in this algorithm, we are putting them in a ring, which means that one node is going to communicate with only one more node, and these nodes, the distance, the number of hops will be taken care of by the reliable multicast. Therefore, we say that we know the amount of time, we can calculate the amount of time communication will take if any node like our P30 starts an election message, then we know that it will do the whole round around the ring and will come back to P30 or go through P30 in a finite time. So, therefore, our liveness criteria says that we should be able to elect a coordinator in finite time. And the other problem of liveness is what happens if one particular node forgets to reply or does not reply. But again, in a reliable multicast, we have ensured that the node, if the node has to send a reply or is required to send a reply, then it will definitely send a reply, and that too not in an infinite time, it will send within a finite time. So, our using of reliable multicast ensures liveness in our election algorithm. Now, let us look at safety. So, what is the guarantee that only one process will be elected as a leader? Now, it depends on the criteria that we are setting. What is our criteria in the example that we have given? Our criteria is that the highest priority process, highest ID, having the a process having the highest ID, and we said that all the processes have unique ID. So, if processes are having unique ID and we are going to take the highest ID process as the coordinator, then obviously there will be only one process that will be elected. Safety can also be looked at by saying other criteria. Say if we put some other criteria like process having the maximum amount of memory, or a process having maximum number of requirement, or maybe a process having least amount of queue on its CPU. That is the least amount of load. Maybe we want to select the least loaded process. The mechanism has to be such that the value should be unique. Now, if the value is unique, that's the criteria that we are setting, if that criteria is unique, then obviously in the whole system there can be only one such node, and therefore safety is guaranteed. However, the question that we have to look at or we have to ponder is what happens if more than one process starts election together. Do we have a problem of our safety criteria if two or more processes start the election? But how is it possible that two processes will start the election, or maybe 3 or 4, or even is it possible that all n-1 processes will start the election? Yes, it is possible that more than one process will start the election algorithm together. Assume that we are in the process of updating say marks by many peers. All the teachers are trying to update marks from so many client machines, and there is one leader who is going to take all the updates and will store the updates. So, if all of them are trying to contact the leader and the leader has crashed, then all of them together will decide, or maybe 2 or 3 of them together will decide that there is no leader at this point in time. So, it is quite possible that election can be started by more than one process. We will in the next lecture, we will look at this problem and we will try and resolve this problem. In summary of this module, what we look at is that leader election is a very important component. Specifically, leader election, we will see in our later module that election is a very important component for cloud, because every work is done by in data centers in cloud, and data centers consist of many servers which are quite similar to each other. We can say that these are all peers, which means that there is no specific one specific server which is of higher capability or anything. So, among these peers, work can be done, work can be shared by all the peers, but even then many applications are there where we need one of these peers to act as the leader. So, therefore, we need election algorithm for the cloud very specifically. There are classical leader election protocols that have been developed to be used in a generic distributed system, and today we looked at the ring based algorithm where the processes will be put in a logical ring. Again, we must insist that it is not a physical ring, it is a logical ring, which means that physically we are not going to restrict where the peers will be, but only the communication will be restricted, which means that the specific process will be made in such a way that it will only communicate to one other specific process and it will receive messages from the another process. So, that will be the logical ring, and using this logical ring structure we are able to implement the ring based algorithm, and then we have seen that election can be done in finite time and we can elect one leader, one specific leader. The algorithm is correct because we have set the finite time and we select only one leader at a time. These are our references. Thank you.